All right, we're doing this a little haphazard because I don't have necessarily a plan about how to teach all this stuff. So here comes the next video. I've been trying to get something together and just haven't spent as much time as I should planning. But let's talk about some AC circuits, and let's talk about what the alternating current does, what it means. So here's an AC voltage source. It's just drawn as a circle with a little single period of a sine wave in here. Okay, and that single period of the sine wave is representative of what's going on, and here we've designated our frequency, which is 60 hertz. That means 60 cycles in a second. So if you wanted to find out how long a cycle would take, you would divide 1 second by 60 cycles, and it would give you an answer which I believe is either 8 milliseconds or 16 milliseconds. I don't remember offhand. I don't have a calculator handy, so we're going to go ahead and just trust that. 120 volts here is what we've called the root mean square. And again, what that means, we call it RMS, obviously. I don't even know if you can see that on the video, but our RMS voltage, this is 120 volts RMS. And what that means is, if you take a look at the entire path of the voltage right here, and this would be your voltage, this would be your peak right here at a certain amount of voltage. We're going to say 170 because that's what it is. And here's a peak of 170 negative. Okay. Then if you take the area under this curve using calculus and get a mean value. Okay, if you were to do a mean value from the positive and the negative during this cycle, you would wind up with an absolute average of 0, because this point would offset the peak negative, the median here, the middle value here would offset this negative middle value. Of course, what's going to do is it's going to all offset. So instead of doing that way to try and get an average value, what they do is they square every value so that they all add together. You get a cumulative total, and then they add them together, they average it out, get a mean of those squares, and they square root that to get it back down to a close number. And anyway, the simple way to do this is root mean square is basically your peak voltage divided by the square root of 2. That's simple. And if you want to convert from RMS back to peak voltage, you just multiply by the square root of 2. But what we're doing here is we're watching current as it turns around. See, here there is no current with 0 voltage. And then as we get to a peak positive, we're going to call this positive and this negative. We're now moving current this direction. The current goes through the circuit, and I've drawn 3 different components. Okay, here's the resistor, which you should be familiar with by now. This is an inductor right here. And this is a capacitor. Okay, and we'll talk about these in just a second. It pushes current through until it gets to a maximum of 170 volts, where it's really forcing the current through with a lot of force, a lot of potential. And you can think of it again as pressure. The current goes through the entire circuit back to the negative terminal, all the way until we get to the 0 right here. When you reach this 0 amount right here, again there's no current, and then current switches itself. This becomes positive, this top part becomes negative, and we're forcing current the other way. And we look at all of that as a negative just because it's an opposite direction. It's still positive voltage, it's still positive potential, it still forces current to flow in a certain direction. We're just designating negative and positive so we understand that we are alternating which way the voltage is going, and therefore which way our current is flowing. So as we take our negative potential and we force it this way, things are going to change. Well, let's take a look at the components we have in here. We're not going to go into solving for impedance, but basically the way that these components respond to an alternating current varies according to the frequency. Here's why. The inductor is just a coil, and I've drawn here a mock-up, a very bad mock-up drawing of what an inductor looks like. You might have any kind of core in here that's a metallic core, some kind of magnet, ferrous material, and then you wrap a wire around it again and again, and you have an inductor. Every inductor that's made is going to be able to be tested out at some kind of value of how much the electromagnetic field that is created, because remember, this is magnetism. We're moving electrons through here. This is negatively charged particles that are moving through here. And while we're not going to deal with the physics of how this happens, it does create a magnetic field, kind of like this. For this would be the North Pole here, and the South Pole here, the way I'm drawing it. It could be the other way, depending on how current's going, depending on what's going on with the direction of the coil. Lots of things can affect that. But the bottom line is you wind up with a magnetic field, and this magnetic field, remember, you have magnetic particles, magnetically charged particles and electrons moving through a magnetic field. It's going to disturb your current flow, and it acts as basically a resistance. So here you have what's called impedance, which is represented by a Z, and it's only an occurrence for AC circuits. Only if you have an alternating current are you going to deal with impedance, okay? But the impedance basically changes because, the field that you see here at the peak voltage here will be exactly the opposite of the field that you would see here during the peak negative voltage here. And also, if it's changing through a full cycle from 0 to positive to 0 to negative peak to 0, 60 times in a second, that you can't keep track of any certain place that field is. And so with that field constantly changing values, we're going to represent it with an impedance value, okay? And I'm not going to go into any of that, or just know that that exists, and later on if you want to, you can do some more research on impedance. But that's how an inductor affects current flow. Now, an inductor is a coil of wire, so it's going to have a natural resistance to flow too, just because it is a certain material. It's made of a physical material that is going to oppose current flow, like friction opposes, you pushing a object across the floor. If you're going to push a box across the floor, friction will oppose that. Well, this will oppose current physically too. That's another property of the inductor, but it's separate. The inductor's magnetic opposition to force is how we create impedance in an alternating current circuit. Here we have a capacitor, and a capacitor you can think of just as two gigantic metal plates set against each other, except they're not actually touching. You could think of just a little thin layer in between them, okay? So I've drawn a representation, a very poor representation of a capacitor right here, and saying that current is flowing this direction. Remember, current is negatively charged particles flowing. So what's going to happen is negatively charged particles are going to pile up here, okay? And the more negatively charged particles that we get piling up here, the more of the negatively charged particles that began over here are going to be repelled and run off. And this is going to fill up with only positively charged particles here, okay? And this will start this direction. Now think about this. The current and the voltage, everything is going to change. At any given point in time, everything will be different. So if we start here at 0, wherever this thing was is where it is left to now. But when you get to a positive peak and current's going this way as hard as it can, you're going to wind up with a maximum amount of charges pushing this way, piling up onto this capacitor and shoving all of the electrons off this way. So remember, current doesn't actually flow through the capacitor. It just is seen across a capacitor because of the repulsion of all these charges piling up on one side and repelling them from the other. The other thing that happens is as soon as this voltage turns around, and now we have a current that's trying to go this way, now we have all these negatively charged particles getting shoved back this way, and they're going to repel all these negatively charged particles from this side of the capacitor out. And what the capacitor does is stores a charge, but if you can think about this, when you first start, this entire plate here is wide open to receiving charges. Everything's available, all of its space is available. It will receive as many charges as you could possibly pile up there to a certain amount. Now, that is going to change when we turn our current around. So the faster that you are turning current from this way, back this way, and back this way, and back that way, the faster that you do that, the less charge this thing is going to build up, because as soon as it starts getting charged in this direction with negatively charged particles, and all these are getting ran off, the very second that that thing starts getting charged, it comes back this way, because the voltage turns around, therefore the current turns around, and all the electrons are being pushed the other way. Well, as you can imagine, if this has a ton of electrons built up on here, that's going to oppose current, which is how you have impedance in a capacitor, okay? And it's a different type of impedance. This is actually called capacitive reactance, which is represented by XC, whereas we had inductive reactance represented by XL for our inductor. Okay, that has to do with the electromagnetic field. This has to do with this charge built up, stored in a capacitor. Our capacitive reactance, the impedance created by a capacitor, if you just pile up charges here and pile up charges here, eventually it's going to get hard to push charges this way because they have to fight through all of these negatively charged particles, and we know that like charges repel each other. Meanwhile, the other way, your capacitive reactance, the total opposition to flow created by a capacitor's charge, will be very minimal if you are turning the current around at, say, 3 megahertz. If you're turning current around 3 million times a second, the charges never have a time to really build up a very large charge on either side of the plate. So that's what's going to happen. So this is a capacitor, that's an inductor, you know what a resistor is. You know the alternating current's going to start one direction, it's going to turn around, it's going to go the other direction. You know what 120 volts looks like at a peak when you take it and you multiply it by the square root of 2 to go from your root mean square, your RMS at 120, to your 170, it's like 169.7 something volts is what you get at peak if you multiply 120 by root 2. And if you take that 169.7 and divide it by the square root of 2, you'll wind up with 120 volts. That's your RMS reading because, again, you can't measure a single constant current or a single constant voltage in an alternating current system because it changes so fast. So this has just been a basic introduction to some of the components and some of the ideas of alternating current, and in one of the later videos we'll get into some more detail and some of these things and how they affect your troubleshooting as a maintenance person.